Well, last time, Jerry really let the cat out of the bag. He introduced the idea of assignment. And state. And as we started to see, the implications of introducing assignment and state into the language are absolutely frightening. I mean, first of all, the substitution model of evaluation breaks down. And we have to use this much more complicated environment model and this very mechanistic thing with diagrams, even to say what statements in the programming language mean. And that's not a mere technical point. See, it's not that we had this particular substitution model and, well, it doesn't quite work, so we have to do something else. It's that nothing like the substitution model can work. Because suddenly a variable is not just something that stands for a value. Right? A variable now has to somehow specify a place that holds a value, and the value that's in that place can change. Or, for instance, an expression like f of x might have a side effect in it. So if we say f of x and it has some value, and then later we say f of x again, we might get a different value depending on the order. So suddenly we have to think not only about values, but about time. And then things like pairs are no longer just their cars and their critters. A pair now is not quite its car and its critter, it's rather its identity. So a pair has identity, it's an object. And two pairs that have the same car and critter, well, might be the same or different, because suddenly we have to worry about sharing. So all of these things enter as soon as we introduce assignment. See, this is a really far cry from where we started with substitution. Right? It's a technically harder way of looking at things because we have to think and more mechanistically about our programming language. We can't just think about it as mathematics. It's philosophically harder because suddenly there are all these funny issues about what does it mean that something changes or that two things are the same. And then also it's programming harder because, as Jerry showed last time, there are all these bugs having to do with bad sequencing and aliasing that just don't exist in a language where we don't worry about objects. Well, how did we get into this mess? Remember what we did. The reason we got into this is because we were looking to build modular systems. Right? We wanted to build systems that fall apart into chunks that seem natural. So for instance, you want to take a random number generator and package up the state of that random number generator inside of it so that we could separate the idea of picking random numbers from the general Monte Carlo strategy of estimating something and separate that from the particular way that you work with random numbers in that formula developed by Cesaro for pi. And similarly, when we go off and construct some models of things, if we go off and model a system that we see in the real world, we'd like our program to break into natural pieces, pieces that mirror the parts of the system that we see in the real world. So for example, if we look at a digital circuit, we say, gee, there's a circuit, and it has a piece, and it has another piece. And these different pieces sort of have identity. They have state. And the state sits on these wires. And we think of this piece as an object that's different from that as an object. And when we watch the system change, we think about a signal coming in here and changing a state that might be here and going here and interacting with a state that might be stored there. and so on and so on. Right. So what we'd like is to build in the computer systems that fall into pieces that mirror our view of reality, of the way that the actual systems we're modeling seem to fall into pieces. Well, maybe the reason that building systems like this seems to introduce such technical complications has nothing to do with computers. See, maybe the real reason that we pay such a price to write programs that mirror our view of reality is that we have the wrong view of reality. See, maybe time is just an illusion, and nothing ever changes. See, for example, if I take this chalk, we say, gee, this is an object, and it has a state. Right? At each moment, it has a position and a velocity. And if we do something, that state can change. But if you studied any relativity, for instance, you know that you don't think of the path of that chalk as something that goes on instant by instant. It's more insightful to think of that whole chalk's existence as a path in space-time that's sort of all splayed out. Right? There aren't individual positions and velocities. There's just its sort of unchanging existence in space-time. Similarly, if we look at this electrical system, if we imagine this electrical system as implementing some sort of signal processing system, the signal processing engineer who put that thing together doesn't think of it as, well, at each instant there's a voltage coming in, and that translates into something, and that affects the state over here, which changes the state over here. Nobody putting together a signal processing system thinks about it like that. Instead, you say there's this signal that sort of is splayed out over time, and if this is acting as a filter, this whole thing transforms this whole thing to some sort of other output. Right? You don't think of it as what's happening instant by instant as the state of these things. And somehow you think of this box as sort of a whole thing, not as little pieces sending messages of state to each other at particular instants. Okay. Well, today we're going to look at another way to decompose systems that's more like the signal processing engineer's view of the world than it is like thinking about objects that communicate sending messages. Okay? That's called stream processing. And we're going to start by showing how we can make our programs more uniform and see a lot more commonality if we throw out of these programs what you might say is an inordinate concern with worrying about time. All right, well, let me start by comparing two procedures. The first one sort of does this. We imagine that there's a tree. Say there's a tree of integers. It's a binary tree. Let's see, 1. So it looks like this, and there's integers at each of the nodes. And what we would like to compute is for each odd number sitting here, we'd like to find the square and then sum up all those squares. Right, well, should be a familiar kind of thing now. There's a recursive strategy for doing it. Right, we look at each leaf, and either it's going to contribute the square of the number if it's odd or 0 if it's even. And then recursively we can say at each tree the sum of all of them is the sum coming from the right branch and the left branch, and recursively down through the nodes. And that's a familiar way of thinking about programming. Let's actually look at that on the slide. Right, we say to sum the odd squares in a tree, well, there's a test. Either it's a leaf node, we're going to check to see if it's an integer, and then either it's odd, in which we take the square, or else it's 0, and then the sum of the whole thing is the sum coming from the left branch and the right branch. Okay, well, let me contrast that with a second problem. Suppose I give you an integer n, and then some function to compute of the first of each integer in 1 through n, and then I want to collect together in a list all those function values that satisfy some property. That's a general kind of thing. Let's say, to be specific, let's imagine that for each integer k, we're going to compute the kth Fibonacci number. And then we'll see which of those are odd and assemble those into a list. So here's a procedure that does that. Find the odd Fibonacci numbers among the first n. And here is a standard loop the way we've been writing it. This is a recursion. Right? It's a loop on k and says if k is bigger than n, it's the empty list. Otherwise, we compute the kth Fibonacci number, call that f. If it's odd, we const it on to the list starting with the next one. And otherwise, we just take the next one. And this is the standard way we've been writing iterative loops, and we start off calling that loop with 1. Okay. So there are two procedures. These procedures look very different. They have very different structures. Yet, from a certain point of view, those procedures are really doing very much the same thing. So if I was talking like a signal processing engineer, what I might say is that the first procedure, this first procedure enumerates the leaves of a tree. And then we can think of a signal coming out of that, which is all the leaves. We'll filter them to see which ones are odd, put them through some kind of filter. We'll then put them through a kind of transducer. Namely, for each one of those things, we'll take the square, and then we'll accumulate all of those. We'll accumulate them by sticking them together with addition starting from 0. That's the first program. The second program I can describe in a very, very similar way. I'll say we'll enumerate the numbers on this interval, so the interval 1 through n. We'll, for each one, compute the Fibonacci number, put them through a transducer. We'll then take the result of that and we'll filter it for oddness. And then we'll take those and put them into an accumulator. This time we'll build up a list, so we'll accumulate with const starting from the empty list. Okay. So this way of looking at the program makes the two seem very, very similar. The problem is that that commonality is completely obscured when we look at the procedures we wrote. Let's go back and look at sum odd squares again and say things like, where's the enumerator? Right, where's the enumerator in this program? Well, it's not in one place. Right, it's a little bit in this leaf node test, which is going to stop. It's a little bit in the recursive structure of the thing itself. Right? Where's the accumulator? The accumulator isn't one place either. It's sort of partly in this 0, right, and partly in this plus. Right? It's not there as a thing that we can look at. Similarly, if we look at odd fibs, that's also, in some sense, an enumerator and an accumulator, but it looks very different because partly the enumerator is here in this greater than sign in the test, and partly it's in this whole recursive structure in the loop and the way that we call it. And then similarly, that's also mixed up in there with the accumulator, which is partly over there and partly over there. Okay? So these very, very natural pieces, right, these very natural boxes here don't appear in our programs because they're kind of mixed up. The programs don't chop things up in the right way. See, we don't have, going back to this fundamental principle of computer science, that in order to control something, you need the name of it. We don't really have control over thinking about things this way because we don't have our hands in them explicitly. We don't have a good language for talking about them. Well, let's invent an appropriate language to which we can build these pieces. The key to the language is to say, is these guys, is what is these things I called signals? What are these things that are flowing on the arrows between the boxes? Okay. Well, those things are going to be data structures called streams. That's going to be the key to inventing this language. What's a stream? Well, a stream is, like anything else, a data abstraction. So I should tell you what its selectors and constructors are. Well, for a stream, we're going to have one constructor that's called constStream. ConstStream is going to put two things together to form a thing called a stream. And then to extract things from the stream, we're going to have a selector called the head of the stream. So if I have a stream, I can take its head, or I can take its tail. And remember, I have to tell you George's contract here. Tell you what the axioms are that relate these. And it's going to be for any x and y, if I form the constStream and take the head of constStream of x and y is going to be x, and the tail of constStream of x and y is going to be y. So those are the constructor, two selectors for streams, and an axiom. There's something fishy here. So you might notice that these are exactly the axioms for const, car, and cdr. See, if instead of writing constStream, I wrote const, and I said head was the car and tail was the cdr, those are exactly the axioms for pairs. And in fact, there's another thing here. We're going to have a thing called the empty stream. Just like the empty list. So why am I introducing this terminology? Why don't I just keep talking about pairs and lists? Well, we'll see. For now, if you like, why don't you just pretend that streams really are just a terminology for lists? And we'll see in a little while why we want to keep this extra abstraction layer and not just call them lists. Okay, now that we have streams, we can start constructing the pieces of the language to operate on streams. And there are a whole bunch of very useful things that we could start making. For instance, we'll make our map box, right? To take a stream S and a procedure, and to generate a new stream which has as its elements the procedure applied to all the successive elements of S. In fact, we've seen this before. This is the procedure map that we did with lists. And you see it's exactly map, except we're testing for empty stream. Oh, I forgot to mention that. Empty stream is like the null test. So if it's empty, we generate the empty stream. Otherwise, we form a new stream whose first element is the procedure applied to the head of the stream, and whose rest is gotten by mapping along with the procedure down the tail of the stream. So that looks exactly like the map procedure we looked at before. Here's another useful thing, filter. This is our filter box. We're going to have a predicate and a stream. We're going to make a new stream that consists of all the elements of the original one that satisfy the predicate. It's case analysis. If there's nothing in the stream, we return the empty stream. We test the predicate on the head of the stream, and if it's true, we add the head of the stream onto the result of filtering the tail of the stream. And otherwise, if that predicate was false, we just filter the tail of the stream. Right, so there's filter. Let me run through a couple of more rather quickly. They're all in the book, and you can look at them. Let me just flash through. Here's accumulate. Accumulate takes a way of combining things and an initial value and a stream and sticks them all together. If the stream's empty, it's just the initial value. Otherwise, we combine the head of the stream with the result of accumulating the tail of the stream starting from the initial value. So that's what I'd use to add up everything in the stream. I'd accumulate with plus. How would I enumerate the leaves of a tree? Well, if the tree is just a leaf itself, I make something which only has that node in it. Otherwise, I append together the stuff of accumulating the left branch, of enumerating the left branch and the right branch. And then append here is like the ordinary append on lists. You can look at that. That's analogous to the ordinary procedure for appending two lists. How would I enumerate an interval? This will take two integers, low and high, and generate a stream of the integers going from low to high. And we can make a whole bunch of pieces. Right, so that's a little language of talking about streams. Once we have streams, we can build things for manipulating them. Again, we're making a language. And now we can start expressing things in this language. Here's our original procedure for summing the odd squares in a tree. And you'll notice it looks exactly now like the block diagram, like the signal processing block diagram. So to sum the odd squares in a tree, we enumerate the leaves of the tree, we filter that for oddness, we map that for squareness, and we accumulate the result of that using addition starting from 0. So we can see the pieces that we wanted. Similarly, the Fibonacci one, right, how do we get the odd fibs? Well, we enumerate the interval from 1 to n. We map along that, computing the Fibonacci of each one. We filter the result of those for oddness. And we accumulate all of that stuff using consts starting from the empty list. Okay. What's the advantage of this? Well, for one thing, we now have pieces that we can start mixing and matching. So for instance, if I wanted to change this, if I wanted to compute the squares of the integers and then filter them, all I need to do is pick up a standard piece like this, a map square, and put it in. Or if we wanted to do this whole Fibonacci computation on the leaves of a tree rather than a sequence, all I need to do is replace this enumerator with that one. See, the advantage of this stream processing is that we're establishing, this is one of the big themes of the course, we're establishing conventional interfaces. Conventional interfaces that allow us to glue things together. Things like map and filter are sort of a standard set of components that we can start using for pasting together programs in all sorts of ways. Right? It allows us to see the commonality of programs. I just ought to mention, I've only showed you two procedures, but let me emphasize that this way of putting things together with maps, filters, and accumulators is very, very general. It's sort of the generate and test kind of paradigm for programs. And as an example of that, Richard Waters, who's at MIT, when he was a graduate student, as part of his thesis research, went and analyzed a large chunk of the IBM Scientific Subroutine library and discovered that about 60% of the programs in it could be expressed exactly in terms using no more than what we've put here: map, filter, and accumulate. All right, let's take a break. Okay. Questions? Yeah.
It seems like the essence of this whole thing is just that you have a very uniform, simple data structure to work with, the stream.
Right. The essence is that it's this sense of conventional interfaces. So you can start putting a lot of things together, and the stream is the sort of, as you say, the uniform data structure that supports that. This is very much like APL, by the way. APL is very much the same idea, except in APL, instead of the stream, you have arrays and vectors. And a lot of the power of the APL is exactly the same reason of the power of this. Okay, thank you. Let's take a break.